Right, let's do another problem. So, today we're going to be working on, for our second problem, 981 time-based key value store. So, another sort of data structure design thing similar to, I think the only other problem that we've had for this was min stack? Was there another system design question? I think there might have been another one that existed within the easies. I think it was like making a queue from a stack or something like that, right? In any case, design a time-based key value data structure that can store multiple values for the same key at different timestamps and retrieve the key's value at a certain timestamp. So implement the time class, so time map initializes, okay. Set stores the key with the value at the given timestamp. Returns a value such that set was called previously with timestamp previous less than the timestamp that we provided. If there are multiple values, it returns the value associated with the largest timestamp previous. If there are no values, it returns that. Do we have a constraint as for runtime? Doesn't look like it. Interesting. So we set, let me map this out. Set inserts a key and a value at a specific timestamp. Get returns the most recent item or no item at all. Will set always be no item at all? We can assume maybe that if an item does not exist of that key, or if no items have a timestamp less than or equal to provided timestamp. So the problem in this case really comes down to the fact that we want to optimize for this get operation such that we don't take long to retrieve the max. Of course, we could just do, well, first of all, I think it's pretty straightforward that the base data structure will be a hash map. I think this sort of key value store pretty much just screams hash map, with the key as a string. The value will also be some sort of data structure. Now, the straightforward answer is a list, right? We just store them. Actually, sure, we can store it as a list of, we can call them nodes, right? Where each node holds a value and a timestamp. Pretty straightforward stuff. We just create a sort of plain old Kotlin object, a POCO, if you will, that just stores the value and the timestamp. Every get request will scan through the nodes, or yeah, the list of nodes, and collect the maximum, which is less than with a timestamp less than provided. Again, this is pretty straightforward stuff. This is linear time, right? Iterating through a list. There's no particular order that we really care too much about. The interesting thing comes then if we want to optimize it. Now, the question really comes down to how can we optimize this? Right? Because this is fine, but potentially we could do better. Well, what are some things that we could do? We need something sequential. So this would be an array, a linked list, a binary tree, heap, etc. We probably don't want something like a set or a hash map within for our internal data structure because there's no easy way of maintaining a different order. In the case of the set, it's the order in which we insert them, but the timestamp that we provide may be in the future or maybe in the past, right? There's no guarantee that the timestamps that we insert in will be all the timestamps of set are strictly increasing. Okay. That's one of the constraints. Again, webcam is kind of hiding it, but all the timestamps of set are strictly increasing. So in that case, every item that we insert will be the item that we actually want to retrieve. Not quite. Because we could always request a timestamp of an item which is less than that. Right? Even though we insert new items. So these insertions, so what that tells me is that insertions will always be made probably to the end of an insertions will probably be made to the end of a data structure in order to preserve the sort of order, I guess you could say, of this. In that case, well, what could we do? A list may be possible to be optimized. And what I say by maybe is that if we know that each item we insert will always be newer than the items before, then we could potentially run some sort of binary search on it. The problem is that our parameter may not necessarily exist within our array. Or rather, our timestamp may not necessarily exist, right? We just want to get the item that is the closest without going over our timestamp, but our timestamp may not necessarily exist within our array. And in that case, we would have to modify binary search to a pretty extreme extent, I feel, in order to get the results that we want. Let's say that we can optimize it and that would produce a log n runtime. It would yield a decent amount of complications. What I'm leaning towards is a max heap of some sort. The idea is that if we have a max heap, then we know that the items underneath the current layer will be less than the items underneath our current layer will be less. But is there any ordering to by how much they are less by? Actually, I don't think so. That would be more of a binary search tree. Some sort of order between left and right trees. So that would be a data structure that we could consider, a binary search tree, and we keep track of the most recent node that we've come from, as long as it's less than or equal to our node. If it's less than or equal to what we want, so first of all, if it's greater, then we just go to the left subtree. If it's equal, then we know that that's probably the value, because in this case, it also says that the timestamps are strictly increasing. So if it's equal, then we know that that's the most recent one. If it's less than, then we would probably try to go as much to the right subtree as possible. But then there's also no guarantee that, in this case, that we can build a binary search tree from scratch that will be balanced. Of course, it is very much possible to build a binary search tree from scratch, but to build it in a manner that it is balanced, I believe, is probably out of the scope of this problem. So this would also be O of log n, with also complications. So are there any other data structures that we could probably use? The max heap would be interesting, but I think that in that case we might actually run into yeah, if we had a max heap, we'd probably run into actually a runtime that would actually be even slower if we wanted to search for something that wasn't at the top of the heap. And there's no guarantee that that the timestamp that we search is at the top of the heap. I think actually this binary search idea is actually not that terrible now that I think about it. What this approach would look like is we would say start with the middle of our list in terms of timestamps. If the timestamp, if middle is equal to timestamp, we're done. If middle is less than timestamp, keep it in mind, but go to the right side. If middle is greater than timestamp, go to the left side. And when I say side, I really mean half, right? So for binary search. And this would stop when effectively we get to a situation where left is greater than right, so when they overlap. So that's sort of the idea that we're going for. Let's just quickly do that. Oop. Wrong screen. That's my there you go. That's the VS Code terminal where I just put everything in and stuff it into Git. So I think we can actually go ahead and do that. So for our initialization, we will create a hash map. We'll say, we'll call this data map is a mutable map of, and this mutable map will be of a type string with a mutable list of type data node. And like we said, we'll create a data class data node, which will have a val data of type string, because I just don't want to type val with the little tick marks. And then we can create also a val timestamp, which is of type int. So when we set, the set is pretty straightforward. Data map get or put our key and this get or put, should we do get or put? Let's just do if data map get key val list is data map get key as list or mutable list of data node, because I'm not sure if Kotlin will complain that this is a complex expression again. And then we'll do list add our new data node of value and timestamp. And this will add it to the list. If it doesn't exist, then data map put into key a mutable list of data node, starting with our data node with the value of value and a timestamp of timestamp. So the set functionality is pretty straightforward. If we have a list already, then we'll just append to that list. If we don't have a list, then we'll create a list and we'll insert our data node into it. Don't return anything from there. We don't need to. Now, we can have a var, we can say closest key will be equal to an empty string for now. We can say if data map get key is equal to null, we can just return our empty string. Otherwise, we will return data map get key, or we can get, let's create a new private function, which will really, what do we want here? We don't really care about the key. Well, we actually still need the key. Or actually, no, we don't really need it. We can say the list, which is of a mutable list, or we can say list of data node, because we won't be modifying it. We need our timestamp, which is of type int. We need a low or a left, which is of type int, and a right of type int in order to do our binary search. And we will return a string in this case. And we can just say we will run a get using this array, or this list, our timestamp as per usual, our left of 0, and our right as data map get key dot size. This right edge, as I think most binary search implementations, will be exclusive. Then our middle value will be equal to our right plus left divided by 2. And we can say when our middle dot val, or data, is equal to our timestamp. Because we are strictly increasing, then we know that this timestamp is the most recent without going over. Then we can return the data. If it's less, we need to save our current value, compute a potentially newer value, and check to make sure that it isn't empty. So we can say val, so if our data is less than our timestamp, then we want to recurse on the right side. Right result is a get on the same list on the same timestamp with our left as mid and our right as right. If right result is not empty, return right result. Otherwise, return middle dot data. So we want to return our best, but we don't know if there is a better. If what we find later on is empty, then we don't want to return it. Otherwise, we do something pretty similar here. Actually, we can just return get list timestamp on our left to our mid, exclusive as per usual. And if left is greater than right, return an empty string. So this get means that our data currently is newer than what we want for our timestamp, so we have to go to the left and grab an older version. If our data is lower than our current timestamp, then we can go to the right side and we can try to see if there's a better value. If there is a better value, then we check to make sure that, first of all, this string is not empty. If the string is empty, then we didn't find any better data. And let's see. And if it isn't empty, then we found a better point of data, basically. So let's see if this works. let's run our code first to see if there's any compile time errors. Looks like there's a decent amount. Don't want truthy statements there. Let's see, then our middle.data. Unresolved reference to data. Looks like this, data is a reserved word as well. You know what? Fine. We'll use val. Is there any more areas where we did data? Don't think so. And this size is a complex expression, of course. Inner list is data map.get key as list of data node. And then we do inner list dot size. Did it yell at me for this other situation where... Nope, it didn't. Cool. Alright, let's run our code. Return middle dot val. Data map dot get key. We can do inner list here as well. This mid should be middle. Sure. Looks like this, it's not quite happy about the fact I'm using val here either. I wonder if it'll be happier if I just put it inside this, if I put it inside this class. Maybe it just doesn't work outside the class. At least within the context of LeetCode. Because they might just compile whatever's inside. Looks like they're still not happy. Let's see if value is better. Oh, right. Might be better if I actually got the actual value. Val middle node is equal to list at middle. So I don't want to replace it for the recursive parts. I just want it to for the comparison parts. Is there any still backtick like val? Cool, looks like we got rid of it. Let's see if this still breaks. Value, oh, we want our timestamp actually, not our value. Let's see, and we ran into an out of bounds exception. List middle, right plus left divided by 2. Index is 1, size 1. If we did that and then a set there and then we did a get there, did a set there and a get there. then inner list dot size, that would be 1 plus left, that would be 0. 1 over 2, it should be 0. Let's just toss this up here first. Or is it doing the division before the addition thing again? And we got an overflow error. This middle to the right and the right, we could do middle plus 1 here. And the middle here is exclusive. Let's see. In that case, we throw it in at, we check out the middle, which is 1 plus 0, so that's size 0. And that timestamp should be exactly 1. So why doesn't that return? Unless we're not breaking there. Let's see. We can print middle node. Let's print it out. Because this is a data class, it should print out pretty nicely. Give us some insight into this. I could say print line getting closest stamp to timestamp of key. Let's see. Closest timestamp to 3 of key foo. And there's only one item in foo when we do this get. We do a set and then we do 2 gets. The first get is a foo for 1. We return that. The second one is a foo of size 3. Do we want to do less than or equal to right? Less than or equal to right. We can try that. Man, I should really brush up on sort of the foundations of binary search. I think that would be really helpful. There's only one example and it worked. Now that I set it to left greater than right to do that. Let's toss it through a submit then and let's see how we do it. Okay. Really good memory, really bad runtime. Let's see if we can do better on the second submit. Really good runtime, really bad you can't win with LeetCode. But in any case, this was actually a pretty fun problem, just getting to use binary search like this again. You don't get to use it that often, but binary search is one of those very useful things. I think that it was... What I did well was just identifying sort of what we needed out of a data structure within this sort of design problem. Sort of if we really need a sequence to hold, and sort of what algorithms we can use to make this faster. And I think that was pretty good. But in any case, I hope you learned something, and I'll see you for the next problem.